we can have a clocked version of this. What the clock does is works a bit like the Viking longbow drummers. That it provides a timing mechanism to keep everything happening, or all the changes to the outputs happening at the same time. So if I've got several different flip-flops and I want them to change at the moment that I want them to change at, use a clocked or a synchronous.
It's like refreshing it, isn't it?
Sorry?
It's like refreshing it, isn't it? Kind of refreshing the system, because you know, you can change either set or reset high or low, but then when you do have that clock pulse going in at the positive going edge, then it kind of refreshes the system.
It tells you when, or tells the flip-flop when it needs to look at the inputs.
Yeah.
So it's
I kind of see that as refreshing it, sort of.
I suppose, yeah.
Okay. But anyway.
Alright, okay, so a clocked SR has a very similar symbol. Again, we've got Q and Q bar outputs. We've still got our S and our R inputs, but now we've got a clock. So that is the symbol for a clock input. So the clock input is based on, well, for this one, this means a rising edge or positive going edge. Okay, so commonly called PGE. Okay, and what that's looking for is a voltage that goes from low to high very quickly. So it's got to be within a certain amount of time. It can't be a low to high that takes time like that.
If that does happen, does it not change?
It ignores it.
Ignores it.
It doesn't see it as a rising edge. It just sees it as a change in logic, but it doesn't trigger the flip-flop to change. Okay? So the clock here is serving as an indicator for that flip-flop to look at the set or the reset pin. So the truth table for this doesn't change, except if I add my clock pin to my truth table, and I'm only going to include Q now. So I've got my clock, set, reset, and Q. So if it is a falling edge, or let's actually, if it's anything not a rising edge, so not rising edge, I'm going to draw the arrow on my rising edges to indicate that that's what's looking at. So if it's not a rising edge, we don't care what set and reset are doing, we've got no change. Okay? But if we do have a rising edge, and set is 1, reset is 0. Oh, actually I'll include the 0, 0.
Yeah.
Yep, start 0, 0. We still get no change. Put a rising edge here. Set is 1, 0. Q becomes 1. And you can see this is identical in operation to the SR flip-flop that we went through before, except now we have to wait on this condition here. So you can sort of think of it about the flip-flop only looks at the set and the reset pins when it sees this rising edge. Otherwise it ignores everything else. So it won't change until it sees a rising edge. And that rising edge has to be pretty quick. So within a couple of microseconds, I think.
Oh,
so
that's pretty quick.
It is quite quick. That depends on the manufacturer, of course. Okay, so if it doesn't see this, it will not change. And otherwise, if it does, it behaves the same as the SR flip-flop.
So you can see it as an if statement, pretty much.
You could, yes. You could say, if we get a rising edge, then look at S and R, and if S is 1 and R is 0, then set the output to 1.
Cool.
So that is a clocked flip-flop. And if I look at the timing diagram for this, and this is where it becomes really important. So I'm going to have my clock, my set, reset, and Q again. So if clock is doing that, so there's my rising edge, and well, set and reset are both low, and I'm going to start with Q being low. Then at this point here, there's no rising edge, so Q is not going to change. If I have set changing to high there, then the output here doesn't see the rising edge, so it's not going to change yet. Okay, so this isn't going to change until it sees this. So it sees this and it looks at the set and it goes, oh, okay, set's high, so better set Q to high.
Maybe draw a dotted line.
Yep, dotted line to indicate the timing. Okay, so you can see how set has changed earlier than the output has changed by a significant time, because it won't change until it sees this rising clock edge. And something I used to always get confused with was this clock, it could be, doesn't have to be a regular timing thing, it could be manually driven by a switch of some sort or a sensor.
Yeah.
Okay, so the clock here could be as irregular as you like. Could be, you know, 5 now and then 1 in 10 minutes and then 1 in 20 minutes after that. So,
so you could have the controlling method as either yourself or a 5 timer, or
yep, or triple fives, or
what you've explained before,
or a switch. So, for example, I've seen a circuit that uses a couple of reed switches that are clocking flip-flops in order to provide a counter for like a bike trip meter or something like that.
Okay.
So the reed switches, they trigger the flip-flop to change only at a certain time. So I can, again, with this, I can have the set changing a whole bunch of times, and it will not do anything until, and reset can also change a whole bunch of times. The output will not change until we see another rising clock edge. Okay, so now on the rising clock edge, it's going to look at set and reset, and it sees that set is low and reset is high, so the output is going to change from high to low. Okay. So it's important here. The important thing to hear is that the output doesn't change until the rising edge of the clock here. Now, not all flip-flops are rising edge triggered. There are falling edge triggered. Okay, so it has a symbol that looks like this, with a circle in front of it. And this is a falling or negative.
Are they common, like the positive going edge?
Yep, so an NGE triggered flip-flops are quite common. Okay, so yeah, NGE triggered flip-flops are quite common, equally common as positive going edge, I believe. So it just varies depending on the manufacturer, technology being used. Their operation isn't any different, except instead of looking at the rising edge, it would trigger on the falling edge. Okay, so it would be slightly different. Like this timing diagram would work, but the operation is identical, except it's like the inverse of that inverted clock. Okay, so that is the 2 SR types of flip-flop. We've got the synchronous and asynchronous types, and both are equally common, just how they're made. There's another type, called a D type. Okay, which is D can stand for data or delay. And you'll see why these two, why it's called that in a moment. So the symbol is very similar. We've got a D and our clock symbol.
Thanks.
Okay, so we've only got the one input now instead of the two, S and R. And you can think of D as the next Q. So what happens is whatever D is, when the clock sees the appropriate clock edge, so rising edge in this case, Q will become whatever D is. Okay, so if D is high, then Q will be high. If D is low, then Q will be low. So let's have a look at the timing diagram of that, and then I'll look at the truth table. So if I've got my D input, my clock input, and my Q. So if D is high, let's say Q is low, and we see the clock edge, rising edge there, then D is high, so Q goes high at this point. Okay, if D was to be
Oh, I see.
high again, Q would not change. Okay, so Q doesn't change at this time because it's already high. If D is low on this clock edge here, then at this time Q drops to low. Okay, so whatever D is, Q becomes after the next appropriate clock edge.
So what's the purpose of having that? Having D and Q?
You've only got one input, and you can't have that illegal state of both S and R being high.
Okay.
Okay, so the third type of flip-flop is called a JK. JK flip-flop, and that has a symbol. Draw it a bit bigger because it's got a few more inputs. We've still got our two complementary outputs as usual. A J input and a K input and our clock.
Mm-hmm.
Okay, now the J input and the K input, they behave identically to the S and the R for the synchronous flip-flop. Okay, so J will set the output high after the appropriate clock edge. K will set the output high after the appropriate clock edge.
So it's exactly
set
like
the output low after the appropriate clock.
So it's exactly like the SR with the clock
It's
input.
exactly like, except J and K can both be high.
Ah.
Okay, explain what that is in the truth table in a moment. So let's do the truth table for this one. So we've got a J, K, clock, and Q. Okay, and before, if it's not a rising edge, we don't care what J and K are,
No change.
Okay. And if it is a rising clock edge, and these are both 0, again, no change. Right, so if we get a rising clock edge, J is 1 and K is 0,
So that's
Q
one.
is 1. So that sets it. And this resets it. Now here's where it's slightly different. If both J and K are high, for the SR flip-flop, that was an illegal state. The output, we could depend on what the output was going to do. It could be high or low or changing rapidly or doing all sorts of things. So in this case though, we call this the toggle mode. Right? So toggle means it will change regardless of its current state. Okay? So if it was 0, it would become a 1. If it was a 1, it would become a 0. So the toggle state's actually quite important because we'll use this later on when we look at counters. Okay. Now the JK flip-flop has two other inputs, the set and reset.
5 inputs.
Yep, so we've got 5 inputs if you count the clock. And the truth table for that looks a bit like this. So okay, so we've got clock J, K, S, R. Okay. So 0, 0 for the set and reset. So if set and reset are both 0, it's as before. Okay, so meaning what the JK truth table was. Okay. If set is 1, we don't care about these ones. It doesn't even look at them.
Oh.
It instantaneously changes Q to be high. Okay, so the as before was the JK truth table I had before. Now if set is high and reset is low, then we don't care about what the clock and the JK are doing. We change the output to high. Likewise, if reset is high, we don't care about what these two are doing, and we don't care about the clock, we set the output to low. And as for the asynchronous SR, this is invalid if you have both set and reset high. Okay, so both, you cannot have both set and reset high because you won't get an output you can rely on. So we could use this to either wait for our inputs to come in and make the changes happen with a clock pulse, so we can synchronise several parts of our circuit together. Or if I would need to override that for some reason, say I want to reset my counter without having to wait for the next clock pulse, I can reset it.
Yeah.
Or if I want to set it to a certain number, I can set it. So, and that'll happen instantaneously.
It's like an override code, isn't it?
It is an override, if you like. So as before, you can sort of think about them as being a series of if statements. The flip-flop is sort of sitting there looking and it says, okay, if I see set and reset, then I do what this truth table tells me. So if I see set high or reset high, then I go do what this tells me. Otherwise, I then wait until I see a clock pulse. When I see the clock pulse, then do what the truth table told me for the JK. Okay, so the S and the R are asynchronous inputs. The J and the K are synchronous. Okay. So with the JK both being high, this sets this flip-flop to a toggle. So this is how we can make something called a toggle type or a T-type flip-flop. So they don't actually manufacture T-type flip-flops discretely, so you can't go out and buy a T-type flip-flop. You can buy a JK-type flip-flop and wire it to be a T-type. So T-type, toggle.
Because it's a mode, it's not actual a type thing, is it?
That's right. So it's created by wiring a JK. So made using JKs or D type. Okay, so with the JK, all I need to do is set both J and K to high, and it will become a toggle type. I'll draw the truth table for this. Okay, I'm not going to bother with clock and output. So if clock goes from low to high, let's start with the output being low. Let's say it's a rising edge triggered flip-flop, then that'll trigger it to change. And it won't change again until it sees another rising edge. So if I have a clock signal, let's say for the sake of argument it's a regular clock signal, so
it's pretty regular.
We're getting a rising edge every 1 second. Then this output here won't change until each rising edge. So it changes once a second, but it doesn't do a full cycle, so going from low to high, back to low again, and then, so this is one full cycle of our output here. That doesn't change, it changes at half the rate that our clock signal does. Okay, so half the frequency. So Q is half. Okay. Now this has a very important implication for counters. If you recall from the number systems video, if you look at binary, so if let's look at the a 3-digit binary. So that's each possible state for our 3-bit number.
So 2 to 3, which is 8.
Yep. So we've got 0, 1, 2, 3, 4, 5, 6, 7, and then it would go back to 0 again because we've run out of bits. Okay. If you have a look at the patterns here, this one changes from 0 to 1 and back to 0 again every different number. Okay. So there we're going. The change is one every one. It's changing. Okay. The second bit here is only changing every second one. So we're getting 2 in a row, 2 in a row, 2 in a row, 2 in a row. And this third one is changing every 4. Okay, so if you think about this as being these two here, 0, 1, is being this cycle here, 0 to 1, then this one is changing until we've done a full cycle of this one. And likewise, this one isn't changing until we've done a full cycle of this one. So these are half the frequency. So let's put Q1, Q2 and Q4. So my 1s, my 2s and my 4s. My 2s are changing at half the frequency of my 1s, and my 4s are changing at half the frequency of my 2s. Okay? So we can use this T-type flip-flop to create a counter that counts through a binary number. Okay. I'll show you how to wire up a D-type flip-flop to do the same thing. So JK flip-flop is simple, you just wire the J and the K to high and it becomes toggle mode. For a D-type flip-flop, you've got to do something a little bit different.
So there's 2 ways you can do it?
Yeah, there are 2 ways we can make a T-type.
Yeah.
So for a D-type, so using D-types, I take my D-type flip-flop here with Q and Q bar, and there's my D. Now if you remember I said that D you can think of as being next to Q. And if we wanted to toggle after each clock pulse, we want D to be the opposite of what Q is. So the opposite of what Q is, well, we've got that, it's Q bar. So if we wire it like so, connect Q bar to D, then each time this senses a rising clock pulse, the output here is going to change, toggle from what it was. Okay. This is the only way you can wire a D type to be a toggle. Okay, so now let's have a look and see how we can create a counter using this. So remember, we want to have this output here being half the frequency of this clock here, if we have another bit on the on here, we want to be half the frequency of this one, we can use this to clock another T-type flip-flop. Okay? So this one, let's call this Q1 and Q2. Q2 here won't change until it sees Q1 going from low to high. And Q1 will only go low to high after a full cycle of clock. Okay, so to show the operation of a counter, it's best to use the timing diagram. So let's do it over this side. So I've got my clock, I've got Q1, Q2, and let's say that Q1 and Q2 are both low. Okay, and just highlighting my rising edges there. This is where the first flip-flop, Q1, is going to change. So Q1 is going to change from low to high on the rising edge here. Okay, and if you look, Q1 is the thing clocking our second flip-flop there, and we've got a low to high, so that's a rising edge. So let's make, that's going to trigger Q2 to change. Okay, so we started with 0, 0, and after the first rising edge, we're down to 1, 1. So it's actually, this is a down counter. Okay, so we're counting backwards, if you like. We've got to 0, and then we're going back, wrapping back around to
1, 1, 1,
1, 1, which is a logic 3. Okay. If I were to have a third flip-flop on here, let's put that in, wire it in identically. That's Q, oh, I'm going to call it Q4. I'm calling it Q4 because this has got the weights 1s, 2s and 4s. Okay, and still need that. Okay, and Q4, if that started low, that sees a rising clock edge there, so it will change again. So it went from 0, 0, 0 to 1, 1, 1. Okay. Now next clock edge, that causes this one to change, but this is a falling edge, so this Q2 will not change. Now Q2 hasn't changed, Q4 is certainly not going to change. See a rising edge here now, so it causes Q1 to go from low to high, which is a rising edge for Q2, so that will change. And this is a falling edge for Q4, so that's not going to change. Okay, so you can see here that we've got 0, 0, 0, which equals 0. We've got 1, 1, 1, which is 7. And we've got 1, 1, 0, which is 6. And then we've got 1, 0, 1, which is 5. So you can see that this is now counting down as my clock pulses advance. Okay. So this is how a 3-bit down counter. Now I can change this to be, instead of a down counter, to be an up counter. And that's pretty straightforward. There's 2 ways I can do it. Well, there are 3. 2 easy ways that I can do it by rewiring. Mm-hmm. The third way is to change these from being positive going edge flip-flops to negative going edge flip-flops. But that's quite difficult because it usually requires changing the type of circuit that you use altogether. So I would generally say that is not an option. If you've selected your flip-flops, just rewire it. It's easy to rewire it. Okay, so if I then looked at, instead of looking at Q1, Q2 and Q4 as being my outputs, so what I'm saying here is that I'm connecting this to my that's Q1, that's Q2, that's Q.
Couldn't you include clock as a cue as well?
I could, but I want this thing to be able to hold its state. So if I want my counter to stop,
right, yeah.
I can't control the clock necessarily,
Yep.
but I can control the counter. Okay, so if I can isolate the clock somehow, then I can do it that way.
All right.
Okay, and I want it to remember its state. If I isolated the clock, it would either be 0 or high or something else.
And it's unreliable by a bit.
Unreliable.
Yep.
So this, I want it to be able to hold its state. So I have the outputs of my flip-flop. You remember that I said that a memory device, I wanted to remember the number I've got up to. Okay. So at the moment I've got all my cues. So my normal outputs being the output. I don't have to have that though. I could have Q bar as being my output. So let's have a look and see what would happen if I had Q bar as being the output. So if I'm using Q bar, so that's going Q, not Q1, then not Q2, and not Q3. Okay. So before
you mean 4, isn't it?
Sorry, yeah, Q4, not Q4. Thank you. Before I had 0, 0, 0. If for my Qs, so the output is going to be 1, 1, 1 in this case. So let's just redo it. So 0, 0, 0, then this is 0, 0, 1. And then this is 0, 1, 0. And you get the idea. So 0, 0, 0, 0, 1, 2. 2. So this is an up counter. So I've changed it. I haven't even rewired my circuit. I've just simply changed which output I'm looking at. Instead of looking at my Qs, I'm looking at my not Qs as being my outputs for my number. Cool. Here is a diagram that I prepared earlier.
Yep.
Okay, now the other way I can change it from being an up counter to a down counter is I can change how I'm clocking it. So I don't have to clock off Q, I can clock off Q bar. So if I clocked off Q bar, let's draw that. Okay, so this type of counter is called a ripple counter. And you can think about what's happening here is that the changes here, as this one clocks, maybe make this one change. It's an up counter, so we might have, at the maximum count, we've got 1, 1, 1.
Which is 7, yep.
Which is 7. And then it'll count over back to 0 again.
Yep.
And if you think about what happens there, that as this sees the rising clock edge, that causes this to change, which might happen a fraction of a second later. Okay, so it's really small, but it's real.
It's there. Yep.
Okay, so it's called a propagation delay between the input and the output. There's a delay time. Okay, so this is a 3-stage ripple counter, and if we were to take the output off Q, we can work out whether it's an up or down counter by looking at what it would do after one clock pulse. So this is a rising edge clock here. So let's take the output of being 0, 0, 0. And if these are all low, so if Q, Q, Q are low, then this is a rising edge, so this will go from low to high, which is a rising edge for this one. So this goes low to high, rising edge for this one, so this goes low to high. So the next, so we get 1, 1, 1, 1. So this is a down counter. So we're counting from 0, and we're at the lowest number, and we wrap around to the highest number again, which is 1, 1, 1, 1. And then the next change would cause this to go low, which would be 1, 1, 0. Okay, so we've got 0, 7, 6. You can imagine it would keep going until we got to 0 again, and then it would repeat the cycle. And so this is a ripple counter, and a ripple counter is called that because the changes you can see rippling through. This one will change with a small but very real delay before this one, and then this one changes a small delay after this one. Okay, so we're going to change, and if you were to look at it in slow motion, you would see this change, then this change, then this change.
How much of a delay is it?
It's in the order of a few nanoseconds. Depends on the flip-flop. It might even be microseconds. It's very small though.
Yeah.
But if you have some logic on this, so if we were to have a logic where we need not, let's call this one A, B and C. So this is not A, this is not B, and let's use C. So we want something to trigger when this one is high and these are low. So if I ANDed all those together, so not A and not B and C, would give me some output which I'm going to call P. Okay, so not A and not B and C would trigger this. So this would go high when it reached 4. Okay, so when it counted down to 4. But however, this would also trigger on this transition here, because this transition here would give me low, low, and before, in a small fraction of time, before this one had a chance to change to low again, we would have 0, 0, 1. Okay, so we would get our output triggering off this. So a ripple counter may not be ideal because the outputs don't all change at the same time. So we call this an asynchronous counter. You can get synchronous counters.
You could imagine how much of a delay you would have if you had 8 bits, like 8 counters.
That's right. If you were triggering off the first and the last, there might be a very large delay if you had enough bits in your big counter. So there are synchronous counters. Well, here is a picture of a synchronous counter's circuit diagram. Which you can see that it uses logic to control the inputs of each flip-flop, but the clock pins are all connected together. So all the clocks are connected off one flip-flop.
Yeah.
So these are all connected together this way. So that is what the internals of a synchronous counter would look like. However, you buy them in packages that are already made up, and there are several different ones. The example is the 4518. That is a binary coded decimal up counter. So it produces a 4-bit binary coded decimal output from a clock pulse. Okay, it counts up. 0 to 9 is the output.
Yep.
And then it resets. So it uses some logic in there to reset it after it gets to 9, and that is a synchronous counter. So the outputs of that binary coded decimal all change at exactly the same time, or extremely close. There is also, you can get up-down counters, which you can change, you can make them count up or down on with the logic on one of the input pins. And there is also the 4026, which is a direct decade counter, so it counts from 0 to 9, and it has a decoder built into it, so you can power a 7-second display straight on the output.